too bright, isn't it? Alright, okay. Okay, whatever. Whatever. Right, so try to sleep sooner tonight. I think it'd be good for you. Are you like up talking to people as well? Or just watching Netflix?
I was just watching.
Okay, so you weren't keeping someone else awake as well? No, okay. You weren't like, hey Kim, check out Riverdale.
She was awake.
Was she?
Yeah.
Okay, maybe she fell asleep in her room at lunchtime, huh? Okay, so the first question in the exam was the one that we've seen a few times. It was the one with the ball being thrown up in the air. You know that one? And it's thrown vertically upwards. Yeah. So it says it later in the question that this is 1.2 meters, but they don't care about that at the beginning. The first question is they want the maximum height to the top here, and the time to reach the maximum height, and then finally they want to know the velocity when it hits the ground here. So let's look at the maximum height. UVATS. The U is 15.5. The V is 0. The A is minus 9.81. And the T and the S are both what we want. So they ask for the S first. Although I kind of feel like it would be easier to get the T first. Because I can say V equals U plus A T. So T is 15.5 divided by 9.81. Could someone type that in, please? I'll open my calculator too. .58 seconds. And then part 1 is the S, which I'll say, do you know what I'll use? I'll say U plus V over 2 times T. So you still have the answer on your calculator, don't you? Could you divide that answer? Oh no, it's gone, is it?
Yeah.
Divide the answer by 2 and multiply by 15.5. So this was the answer for, yeah. So divide by 2, 12.2 meters. Okay? And the last part was the velocity when it hits the ground, or was it the speed? The velocity. That's important because it means it's negative. Okay. U, 15.5. V we don't know. A we do know. T we don't know. And S we do know. What's the S? Minus 1.2. Do you remember doing minus 1.2? I think a few of you did. I'm looking for the V. So V squared equals U squared plus 2AS. The A is negative and the S is negative. So together they're positive. So plus 2 times 9.81 times 1.2, and then the V is the square root of that. And we have to take the minus answer. Plus 2 times 9.81 times 1.2. 16.2. I think somebody said 16.2 down. Was that you or you? That's fine as well. I think somebody said 16.2 down. You don't have to write the minus. Yeah, questions? You look like you have a question, Matt. Are you sure? Are you sure? Siva? No? Okay. How is that now? That was alright, wasn't it? Yeah? Okay, so next now. So this is the question where I'm asking NCUK to give you an extra 2 marks. Because there are 2 ways to state Newton's second law. You can say force is the product of mass and acceleration, or you can say force is the rate of change of momentum with respect to time. Naturally, everyone went with the shorter definition, but the marking scheme only has the longer definition. But when I look at the question, I can see that there was nothing in the question that said you had to use the longer one. So hopefully they'll agree to give the +2, because I think everybody got that right. I think everybody said force is the product of mass and acceleration. I think what the person writing the question meant to say was state Newton's second law of motion in terms of momentum. Perhaps he meant to say that. Okay. So anyways, we know it. The one that they wanted you to use, although they didn't make it clear, was force is the change in momentum over time. And you can write that out in words. So now part 2. This is kind of a mixed question. It wasn't well answered. A ball of mass 0.26 kilograms is thrown towards a child who's holding a wooden bat. The ball is travelling in a horizontal direction at a speed of 6.85 meters per second. The child hits the ball and it comes back at 7.64 meters per second, and the time is only 125 milliseconds. So the ball is going to the right, then it's hit with a bat, and it's going to the left now. So the child is given it a force. Now, it's only for a small time though, but still. What is the change in momentum? So that's mv minus mu, which is 0.26 minus 7.64 minus 0.26, 6.85. Can you type that in, please? Let's see what we get. Kilogram meters per second.
Negative.
Oh, thank you. Part 2. What is the force? So force is delta P over delta T. So that is minus 3.77 over 0.125. So that's about 26 newtons or something. Oh, what's it? Minus 30.2 newtons. Okay. But there's 2 questions done already. This was not answered well. Do you remember how you did? No. Were you trying to use, I think some people were trying to use F equals MA. That which would have worked actually. Because you have the U, you have the V, and you have the T. So you could get the A and multiply by the M. I think, right? Like, what's the U? 6.85. And the V, minus 7.64. And the T is 0.125. And we would like the A. What gives us the A easily? V equals U plus AT. Like that. So minus 7.65 minus 6.85 over 0.125. What's that there? A is minus
116.
point. Okay. But F is equal to MA, so that's minus 116 times, what did you say the mass was? 0.26. So that should be minus 30.2 newtons. Yeah. So you see, you get the same answer. So what went wrong?
Did anyone get this right?
I think nobody got it right, actually. I don't know why, though. What happened? Like, Matt, what happened?
I don't know.
Well, Did you use UVATS?
I used the momentum.
The delta P over delta T,
That's what I use as well.
and it just didn't get it. Okay.
I forgot.
Might be good to have a look at the papers, bring them to class so you can check. Okay. A3. Oh, but A3 actually was the conservation momentum, which I think was okay, wasn't it? You had your car here of 895 kilograms at a speed of 20.2 meters per second, and then it hits a truck here moving in the opposite direction of 15.4 meters per second, and that's 3740 kilograms. What's the velocity after the collision? Yeah. So that's M1 U1 plus M2 U2, and then they've combined together after the collision. So their total mass is 895 plus 3740 MV. So that over that, please. Really interesting to see if it should be, I don't know. I think it'll be negative. Positive? Okay, 8.53 meters per second. Yeah? It's okay? Part 2 of this question was, what is the loss in kinetic energy? So, the loss in kinetic energy, it had more energy at the beginning. So that's a half m v squared plus a half m v squared. Then we have to minus the kinetic energy afterwards, which will be smaller because it loses some. So that's minus a half m v squared. Okay, can you type that in, and then we have that one finished. What do we get?
A thumb or something. Is that 20.2?
Yes. Oh, it's taking a long time. 45746.
4.
So that's 457 kilojoules. Yeah. And the last part, which I think you all got, is where did this missing energy go? It went into heat and sound. Mostly heat, I would say. Yeah. Okay, I think you all got that. Right, number 4 was a turning force question. You had a seesaw like this, and the pivot was here, and you have a child sitting here, so that was a force of 35 G, and then I think you had the center of gravity, was it, or something? Yeah, here, and that's 8.95 G. This whole ladder was 4.6 meters long. There was something else here as well of 40.5 G, and this distance is 0.85 meters, and this distance here to here is Y. Oh, and this distance here we know is 1.2, and there's another force here, the reaction. So the first part is, what is the reaction? So that's easy, because the reaction has to equal 35G plus 8.95 G plus 40.5 G. So that is 35 plus 8.95 plus 40.5 times 9.81. You can get an answer there. Eight to 8 newtons. Okay. That's the or. Right. Now, where do you want to put the turning point? Because you can actually put it anywhere. Now, at first, I was going to put it here, which I could. But I wonder if it'll be any easier if I put it here. Does it really matter? Well, let me see. I think, did most people put it here? The turning point. I'd say probably so. So we'll take this as the turning point, okay? What distance do we need to know? We need to know this distance, don't we? Do we know how much this distance is? Ugh, no, it's messy. Because it will be 4.6. Well, that would be from here to here. Maybe that would be easier, Siva. Perhaps we could go with. You know what? Let's fill in the distances we do know. So the whole thing is 4.6, which means this will be 2.3 into the middle. So that would have to be 1.1 from here to here to get to the middle, which is 2.3. Yeah? Now that's Y, okay, that's 0.85 from there to there. So if that's Y and this distance is 2.3, this piece here will be 2.3 minus Y minus 0.85. So I'll just put a little arrow there. 2.3 minus Y minus 0.85. What's 2.3 minus 0.85, please? 1.45 minus Y. Yeah? Or did I have it the other way around? 2.3 minus 0. Okay. Right, where do we want to put the turning point? Well, make our lives easier. Is there any way to not have Y in it twice? No, unless I choose one of these as the turning points. I'm thinking so much about it that I would have been finished by now if I just started. I'm just going to take this as the turning point. Something inside me says this would be the easiest thing to do. You can put the turning point anywhere, you should get the same answer, okay? So firstly, this force, clockwise or anti-clockwise? This one. Anti, yeah. This one? Very good. And this one? Clockwise. So these two should equal that one. Okay? So let's calculate. The first one, what's the distance here? It's 1.1 times 35g. And I have another one here, yeah, plus y times 828. That's this one here. That should equal this distance times 40.5g. Now what's that distance? It's y plus that distance, which is 1.45. Is it? Yeah. Ah, I was right to pick this because the y is only in the equation once. Not that it was a problem if it was in it twice, just makes it a little bit easier. Because now all I have to do to finish is say y is 1.45 times 40.5g minus 1.1 times 35g all over 828. This should be a small enough number. Yeah.
0.24.
24 centimeters. Okay, on to number 5 now. I don't remember how well that was answered. A simple pendulum is made by attaching a mass of 0.15 kilograms. Determine the length of the pendulum if its time is 0.895 seconds. So which formula do we need here? It's the T equals, 2 pi root L over G. And we're looking for the L here. So what I'll do is I'll just say that's T squared equals 4 pi squared L over G. So the L is T squared times G over 4 pi squared. So here we get the L is 0.895 squared times 9.81 over 4 times 3.1415 squared. So if we hit all that in on the calculator, we get our answer for 2 marks. Zero point two exact, pretty much.
0.199.
Oh, okay, yeah. Oh, yeah, I think a lot of people got this fine. I remember seeing a lot of 0.199, so I think that was good. Now, the next part was 50-50. Sketch a graph to show how the kinetic and potential energies vary over a full cycle. Energy on the y-axis and displacement on the x. Now, we did this in class, but it was not answered so well. So, this is x in meters, and this is energy in joules, and it goes up to 12 millimeters. So actually, all I'll do is I'll do it in millimeters. Minus 12 to 12. And at the very beginning, when you pull it out to the 12, it has no kinetic energy. So the kinetic energy part goes like this. Oh, sorry, might get the idea. That's the kinetic energy. And the potential energy graph was the opposite. It goes like this. And when it's at the center of its motion, it has no potential energy. And that's the potential energy. And then the total energy will be, well, that should be a straight line. That's the total energy.
I solved this the last question, and I was out of time, so I didn't even see this question.
I skipped this.
Really? Because you remember we did.
Yeah, I remember. I just draw the y and the x axis, but then I just skip it.
I just did a P line, I think.
Yeah, I can't remember someone just doing one of the energy ones.
That was
Yeah. Yeah. did this in class, so I remember drawing it. Okay, so anyways, look, that's that. And then the last part is, what is the kinetic energy? So this one actually, alright, that's a bit interesting. Yeah, I think that was a little bit tricky actually. What's the maximum kinetic energy? Okay, so the maximum kinetic energy is equal to a half m the maximum velocity squared. So we have to figure out what's the fastest it can go. Now the fastest it can go is when it's at the bottom, right? But we have to know what that Vmax is. But thankfully we have a formula for V. If it starts on the out, hang on, let me write this down. We have x equals a cos omega t if it starts on the outside, and V equals minus a omega sine omega t. So that's minus a omega sine omega t. Now we want the max. So what's the biggest that this could be? Well, that's just a omega. So the maximum kinetic energy is is a half amplitude squared omega squared. Do we know the omega? We don't. But we know that t equals 2 pi over omega. So omega is 2 pi over t. So that's 4 pi squared over t squared. That cancels that to make it 2. So the answer is 2m pi squared amplitude squared over time squared. You say that's, in fairness, that's very hard. I don't know if anybody got this. Does anyone remember doing this? I doubt it. So do we know the m? We do. It's 0.15. The pi, of course, is 3.1415 squared. The amplitude is 0.012 squared. And the time is 0.895 squared. Minus 4, and what you say, it's 5.32, so that's 532 times 10 to the minus 6 joules. Yeah, so that's 532 microjoules. What's wrong, Matt? You don't look happy. I understand why. It's a stinky question.
I remember using MVT omega.
Good. Is there any other way you could have done this? See, the only other way I could think of doing this is the maximum kinetic energy is also equal to the maximum potential energy. But you don't know what the height is of the pendulum at the start, so you can't do that. I don't think there's any other way to do it. No, I think it's only this. Do you think you got the right answer? Okay. Okay. The next one I think was okay. It was Young's modulus with stress and strain. So the question was, you have a wire and its length is 1.85 meters, and there's a force applied to the wire of 35 newtons, and the wire extends a distance of 0.78 millimeters. And the first question is, what's the strain? So strain is an extension over length, isn't it? Oh, that's fine. So strain is 0.78 times 10 to the minus 3 over 1.85. that should be a pretty small number.
4.22 times 10 to the power 4. Negative 4.
One of you got the units wrong. What's the units here? Units for strain? Yep, correct. But I think one person said Pascal, and they were thinking of stress. I don't know who. Actually, most people had no trouble with their units. I did, how many exams did I correct? 5, wasn't it? I think for 2 people, I gave them 1 mark deduction because on 1 question they had the wrong units. But only 1, and that only happened, I think, for 2 people. Most people actually had all the right units, so that was a success. Okay. Part 2 is what's the area if the Young's modulus is 10 to the 11 pascals. So what would we say? Young's modulus is stress over strain, and stress is force. So 10 to the 11 is force over area, stress over strain. So actually, what have I got to do? I have to do 10 to the 11 times 4.22 times 10 to the minus 4 and divide by 35, and that's equal to 1 over A. So then if I flip that around, I can get the A. So what's that then? Yeah. Should be pretty small. What did you get, Matt?
I got very big.
Very big. Did you put the minus 1 on after? Power minus 1 after you get this fraction?
8.29.
Yeah.
10 to the 5.7.
Meters squared. That's the cross-sectional area. Grant. Right. 7. Congratulations. It was very well answered for a definition question. What is the internal energy of a system? So I think maybe even everybody said the internal energy, everybody said it in words, but they had the right idea. It's the sum of the kinetic energies plus the sum of the potential energies. So congrats. And the second part you also got, at what temperature is the energy minimum? 0 Kelvin. Yeah, so that was good. That was good. Okay. 8 now. A 9 microfarad capacitor is charged to a potential of 12 volts. What is the charge stored on the plates of the capacitor? So that's Q equals CV, isn't it? So that's 9 times 10 to the minus 6 times 12. 108 microcoulombs? 9 times 12, 108? Yeah? Is that right, Siva? Part 2 is also answered well. What is the energy? And that's a half CV squared. So that's 4.5 times 10 to the minus 6 times 144.
Times 10 to the power negative 4.
6 point
40.
times 10 to the
Power negative 4.
joules. So that's 648 microjoules. Yeah. And the last part, which was answered very badly. So everybody did quite well on these 2 parts because it's straightforward. But the last part, I don't even know if anybody got it right. When a second capacitor is connected in series with the 9, and the capacitor component, did you draw it in parallel?
I remember they asked for the second.
Yeah, that's correct. The voltage here is 12 volts, I think they said. Second capacitor is minus series with 9 capacitor, and the capacitor combination is charged to 12 volts, and the total energy is 4.5 times 10 to the minus 4. What is this? Yeah, what's the C? Now that's kind of hard. The first thing we want to do is combine the capacitors, okay? So how do we combine when they're in series? Yeah, so do you know what? I'm going to call that X. So 1 over C is 1 over 9 times 10 to the minus 6 plus 1 over X, okay? So then C is 1 over that, 1 over 9 times 10 to the minus 6 plus 1 over X. We could simplify that. I'll do that in a moment, okay? Now, what do we know? We know that W equals a half CV squared, okay? Do we know W? We do. And do we know V? We do. Do we know C? We don't. So what I could do, actually, you know what? I'm not going to do that just yet. What I'm going to do instead is say C is W over a half V squared. So I can work out the total capacitance. So that is 4.5 times 10 to the minus 4. 12 squared is 144, and a half of 144 is 72. Okay, so what's that, please? Good, okay. So now that you know the C, you could actually put that back in there. So now you have 1 over 6.25 times 10 to the minus 6 equals 1 over 9 times 10 to the minus 6 plus 1 over X. So you could work out the X. So what you could do is you could do 1 over 6.25 times 10 to the minus 6 minus 1 over 9 times 10 to the minus 6. That gives me 1 over X. But if I flip, I can get the X. So now I have my X. So it should be, yes,
2.05 times 10 to the power of negative 5.
2.05 times 10 to the minus 5 farads. So that is 20.5 microfarads. That was a hard one. Yeah? You think you got it? Okay. Maybe I just don't remember correctly. Maybe you did get it. If you did, you were the only one, I think.
No, I remember 6.25.
Yeah, me too, I remember 6.25. I think it's in the question.
That doesn't mean you got 20.5 at the end, though. Yeah. Well, good job. Okay. No, I don't think 6.25 is in the question. So if you got 6.25, that is promising. So, okay, continue. Yeah. 9 is sketch the graph to show how the amplitude of force oscillation changes near its natural frequency. So, to help you remember here, what you have is you would have something like this. You don't have to draw this, by the way. I'm just drawing this to remind you something. So imagine this is oscillating back and forth. So it has an amplitude. And what you can do is you can grab this and you can shake it. And you're trying to make this amplitude increase. Okay? What we discovered, if you look at the graph, this is the amplitude. And this is your frequency in hertz, we'll say. So, you might remember that I said the way to make the amplitude greatest, well, does anyone remember? Same frequency. So there's some special frequency here, F0, which is the same as this frequency. So that if you can match it, you make the amplitude greatest. If you're less than this, you still make the amplitude bigger, but not as big. And the same goes for here as well. Now we have to kind of think about what happens here. I kind of feel like there's some natural amplitude. Maybe I'll call this A0. This is A0 here. I think the graph might look like this. So you can shake it and it can increase, but not until you're shaken near the natural frequency will you get a lot more amplitude. If you shake it too fast, it's going to stay the same amplitude. If you shake it too slow, it's going to stay the same amplitude. So I think it's going to be this shape. Now actually when I checked the marking scheme, the only thing that they actually cared about in the marking scheme, I think in the marking scheme they drew it like this. So they just wanted to see some kind of quadratic shape marked at some natural frequency. I don't know if anybody, did somebody get that?
Skip this.
You skipped it, okay. Okay. Right, B part. You skipped both your graphs in section A then, huh? The spring is hanging from the ceiling vertically down. And you have a 0.15 kilogram attached. And this causes the spring to extend by 24.5 millimeters. What's the K? So first things first, if it's in equilibrium here, you have a weight and you have an up force from hook, which is K delta X. So of course it must be that K delta X equals this. So K will equal 0.15 G over delta X, which is 0.0245. And that's in newtons per meter. So what's that, please? Yeah, that's it. I remember that actually, 60.1. And then the last part is what's the frequency of the vibration. So the frequency is 1 over the time, and the time is 2 pi root m over k. So this is 1 over 2 pi root k over m, which is, in this case, 1 over 2 pi root 60.1 over 0.15. I think a few of you got this part. See that? Yeah? Yeah. 3.19 hertz. Okay? Yeah? And the last one in section A now, question 10. A cell of EMF 1.62 is connected across a 5 ohm resistor and a current of 0.31 flows through. Okay, so you've got this here, which is 1.62 volts. You've got a small resistor here. It's connected to a large resistor of 5 ohms. And if you were to measure the current, it would come across as 0.31 amps. And the question is, what's the small r? Now, in fact, I think there's possibly even a formula for this one, but you can use Kirchhoff. No, formula's not there, strangely.
Yes, it's there.
Is it? We have I.
The V equals to EMF minus the R.
Yeah. We have I, yeah. I forgot what we're looking for. Small r. We have I. We don't have the V though. You'd have to change it into V equals IR. Yeah, I think I'm just going to use Kirchhoff because I like them so much. So it's 1.62 minus 0.31 times 5, because V equals IR. minus 0.31 or equals 0. But you're right, there's the other formula you could have used that said V equals E minus I or. And this E is 1.62, the I is 0.31, and this B you can get by using I or. But you realise you can get the same equation, so it doesn't really matter anyways. So what I'll do is I'll take that to the right, and then I'll divide by 0.31, and I have my small or. Okay, so what's that now?
0.226.
0.226, thank you. Ohms. Okay. There's a second part, which is the resistivity. When 2 meter length of uniform resistance wire is connected in parallel with the 5 ohm. Okay. 5 ohms. And then it's in parallel, so this is your wire here. The current through the cell increases. Right, okay. So you still have your cell here with the little resistance. Now we've worked out the little resistance, haven't we? It's oh sure, there it is there. There it is there. And what's this? This is 1.62 V. And we stick in a ammeter here, or wherever. And that, we're told, is now 0.456 amps because you connected this extra wire in parallel. Right, so the first question is, what is the resistance here? Okay. So I think the first thing we'll have to do is get the total resistance. So what I'll do is I'll call this one here X, and if I was to picture it together as one resistor, I'll call it OR, if you could combine them. So again, using Kirchhoff, you have 1.62 minus 0.456 big OR minus 0.226 times 0.456 equals 0. Okay? Is that okay? Now, do you understand that that OR is for both of them together, as if they were one? So I want to work out this OR. So that will be 1.62 minus 0.226 times 0.456 all over 0.456. What's that now?
3.33
ohms. But of course that's not what I want. It was the X that I wanted. So now I can say that 1 over 3.33 equals 1 over 5 plus 1 over X. So 1 over 3.33 minus 1 over 5 is 1 over X. So if I flip it, I can get the X. What's that now? No, don't worry, it's not. I thought that at first. But it'll be about a tenth. So it should be about 10. Exactly?
9.97.
Aye, okay, 10. Well, no, 9.97 then. Ohms. And then, lastly, what is the resistivity? So remember, resistance is rho L over A. So resistivity is RA over L, which is 3.33 pi radius squared, and the radius is 0.155 times 10 to the minus 3, all over the length, which we're told is 2. That's the answer. So when you're ready, please. Say that again.
1.36.
10 to the minus 7. We have to think about the units now. 126 micro ohm meters. Yeah. Yeah. You're looking shocked, Matt. It's okay? Did anybody get this?
Is it nano?
Yeah, I should have said something sooner. Thank you. Nano ohm meters. Thank you. Okay. Seems very small, suspiciously small. But I trust you. Okay, B1 now. I think a lot of you chose to do the first question, which was about the heat. So, what is specific heat capacity? I think you all got this. Specific heat capacity is the energy required to heat a unit mass by a unit Kelvin or Celsius or whatever. You all have the idea anyways. 2. Sketch a graph of temperature against time to represent the temperature of a block of ice starting at -5. Starts at -5. As heated until it becomes steam at 100. Indicate, and so on. So, what will happen here is slowly it warms up. Right? And then when it hits 0, what happens? It's flat here. Why is it flat here? Because it's melting. And then it'll heat up till it reaches 100. Then it's flat again for longer than here, which I think a lot of you got. And then it heats up again. So this is vaporization. And this one here is melting. Yeah. And this point here is 100 Celsius. And this point here is 0. And you don't have to say this, but this one should be longer than this one, because it takes longer to turn water into steam than ice into water, because it needs more energy. You know, this one needs megajoules and this one needs kilojoules. Yeah? If you're going to be particular about it, I should actually not have this as steep, so maybe less steep, because ice heats up quicker than water, but I don't think they're that fussy about it, although it is 6 marks. Sorry, until it becomes steam at 105, so I have to stop here at 105. Yeah? Any questions with that? I think that one was okay, wasn't it? Is that why you all did it? A block of copper of mass, this is the third thing that's mass 0.15 in the exam. Mass 0.15 kilograms and a temperature of 20.5 Celsius. It's carefully lowered into an insulated cylinder of liquid oxygen at its boiling temperature. So this is put into boiling liquid oxygen, and it's boiling at -183 Celsius only. Determine the mass of oxygen that is vaporized. So this will turn into steam. So think about it. I know it seems weird, but it's boiling. It's bubbling away, roughly, at -183. So if you give it a bit more heat, it will turn into steam. So this block is very hot compared to its temperature. So what's going to happen is some of this oxygen will turn into gas. How much they want to know? Well, what will happen is your copper block will cool down to this temperature if it's put into the liquid. That means it gains or loses. It loses, yeah. And this has to equal the energy gained by the steam. So basically you've got mc delta theta equals ml, where this is the m of the block, and this is the m of the oxygen. And it's this that we want. So what's the mass? That's 0.15. What's the specific heat capacity of copper? That's 385. What's the change in temperature? It's 183, 203.5, right? I think, yes? That's to equal M, which we want, times L. So if I divide by L, I've got the M. 24.4 times 10 to the 4. And we're done.
Zero point zero four eight.
0.048 kilograms. Yeah. Yeah, okay. C was ideal gas law. So you have your volume. It's 0.146 meters cubed. It contains 3.6 moles of oxygen at a temperature of 20.5 plus 273, so 293.5 Kelvin. Yeah. What's the pressure? So PV equals nRT. So P equals nRT over V. So that is 3.6 times 8.31 times 293.5 over 0.146, please. And then we have that done already.
Six zero one three
60139 pascals, yeah? So that's 60100 pascals. Yeah? It's okay. Part 2, I think you know how to do this. How many oxygen molecules are there? How do you get that? Yeah, moles times Avogadro's constant, which is, what's that, 6.02 times 10 to the 23, isn't it? So what's that, like 18, 19, 19 something? Number of molecules or whatever. Okay. 3. What's the volume? So again, it's another ideal gas law, except they've changed the story. The pressure is now 1.01 times 10 to the 5, and the temperature is 0 Celsius, which is 273 Kelvin. So the P is N, which is still 3.6, R, which is still 8.31, T, which is now 273, and the V is now, oh sorry, no stop, sorry. I got that wrong. PV equals nRT, we're looking for the V. So I divide by P. So that's 3.6 times 8.31 times 273.15 if you want, over 1.01 times 10 to the 5. 0.081 meters cubed. Yeah? The last part is the density. So the density is the mass over the volume. And the nice thing is we know the volume. We have to work out the mass. Now you're told that the relative atomic mass is 16. So are they trying to say that 1 mole is 16 grams? Is that what that is? You're the chemistry students, you can help me out here. Relative atomic mass is 16. I think that means one mole of oxygen is 16 grams. It sounds about right, doesn't it, as well, on your periodic table? So is it just 0.016 16 grams times 3.6 over 0.081?
You have to use square.
Huh? You have to use grams, yeah. Did you have 16 times 3.6?
Yes.
You could have, but then your answer is grams per meter cubed, which is okay. What is this? Actually, you know what? While you're typing that in, Matt, maybe Siba, you could just Google, could you Google density of oxygen at STP? We'll see if we get the same answer. Density of oxygen at STP. What is it?
0.711.
0.711 kilograms per meter cubed.
1.43 grams per liter.
Oh, grams per litre? What the fudge?
Oh, you times 2. Because O2.
Yes, it's there too.
Oh, son of a Newton. Diatomic, isn't it? I forgot about that. Wait, how does that change it?
Times.
The mass times the relative atomic mass.
Yep, it's the same. 1.4 to 1.43.
Oh, because,
Oxygen is 2.
oh man, that sucks. I would have lost that mark in the exam, I think. 1.42 kilograms per meter cubed. And I think you said like 1.4, didn't you? Oh man, I missed that. So that 16 is for O, not O2.
I multiplied it into 0.016.
By 2. It's kind of more of a chemistry question than a physics question. A little bit. But you knew it from chemistry.
I told you.
You didn't do this one on the exam? I think you should have, because you didn't do great on the next one, which is the Newton one with the ladder. Well, I think you would have done better on this one, actually. You see, you made the smart choice here. I think question 1 and 3 were good. I'm actually surprised anybody did this one because of the ladder picture. But you did. Good for you. It's good to try.
I did as well.
You did this as well. You did 1 and 2.
I think everybody did this.
No one did the.
No. A couple of people did 3 and they did fine on it.
Oh,
I did 2 and 2.
Yeah. Yeah. Let's have a look. The first part in B2 is what's the moment of a force. And I think everybody got this right. It was force by perpendicular distance. And I won't bother writing that down, everybody. I think everybody got that. Now, this one here, the ladder one. Okay, let's have a look. So you have a ladder here, and you've got some forces. So you've got this friction force, which is stopping it sliding left. You got this reaction force, which they call N. You got this reaction force here, which they call S. You got this force here, which is 25G. And the ladder's 3.5 meters long. Oh, and This distance here is 1.2. This distance here is, they say, 3.5. This distance here you can get from Pythagoras if you do square root 3.5 squared minus 1.2 squared. What's that, please?
$3.29.
3.29 meters. Okay? Right. Part 1. What is the n? The n is equal to 25g, which is what? I think you got this wrong. No, here. Did you get 245 here?
I forgot.
Huh?
I forgot.
Okay. Well, maybe you did, maybe you didn't. What about the f now? How can we get the f? What do we think? Yeah, problem is we don't know s. So what can we do next? I think we would need to use turning force. Yeah? Yeah? I could use this as a turning point. So if you look here, this is clockwise, this is clockwise, and this is anti-clockwise. So if this is 1.2, then what's this distance here? It's 0.6. So it's 0.6 times 25g plus, and then this is another clockwise one, 3.29 times f. That should equal this one here, which is the full 1.2 times n. 1.2 times 245. So I can say f is 1.2 times 245 minus 0.6 times 25g all over 3.29. You see, that's a bit tricky. What do we get for that? Oh, japers. .6 newtons. Okay, what is the magnitude of the resultant force on the ground? So that's the F and the...
Is there other ways to do it?
Don't really think so. Did you find another way to do it? We can have a look at this later, don't worry. So now we have this here is 44.6 and this one here is 245. And they want the magnitude and the direction. So the magnitude would be square root 44.6 squared plus 245 squared, and the direction would be tan inverse 245 over 44.6. So we have an angle and we have a magnitude. So what's the magnitude? 249 newtons, and the direction? Tan inverse 245 over 44.6. .8 degrees. Yeah? Now, how are we doing for time? We're all right, actually. Might even get the exam finished. Okay. Part C1. Define work. Some of you got this right. Work is force by distance. The force in the direction, the displacement precisely. And 1 joule of work is when 1 Newton is applied over 1 meter of distance. So I won't write that down. I think most of you got this anyways. The second part is more interesting, which is the car. Car's parked at the top of a hill. The car has a mass of 920 kilograms. It falls down the hill, slowly rolls down. The car reaches a speed here of 10 meters per second after it travelled 70 meters, and in the process it lost some potential energy because it's losing height. So the loss in potential energy was 1.85 times 10 to the 5 joules. Okay, so the first question is, what is the vertical distance? Well, that's just good old mgh equals 1.85 times 10 to the 5. Because that's how much potential energy it lost. Wait, hang on. MGH. Yeah, actually they tell us that, don't they? Yeah, so it's just over this. So 20.5 meters is this height here. Okay? What's the kinetic energy gained by the car? Oh, I think they're trying to trick us here. I think those sons of a guns are trying to trick us. I'll explain why in a moment. Anyways, the kinetic energy is a half mv squared. Yeah? So what's that, please? 46,000 joules. That's 0.46 times 10 to the 5 joules. Now the reason I wrote it like this is to point out something. How much potential energy did it lose? 1.85 times 10 to the 5 joules, right? How much kinetic energy did it gain? 0.46 times 10 to the 5 joules. Those numbers should be equal, but they're not. So what's happening is there's some energy being lost through heat. You know, all the potential energy at the beginning was not converted into kinetic energy. If you wrote down the formula mgh equals a half mv squared, you will not get 10 as the answer for v. You'll get a bigger number. So what's happening is some of the energy is being lost, which they never said at the start of the question. In the last part of the question it says, what is the resistive force? So in other words, there's some kind of friction force here that's making heat. So as this is sliding down the hill, there's some heat coming off from this friction force. And they want us to know what this force is. Well, that's a little bit tricky. How could we get that? Well, I think the easiest thing would be to remember that the work done in making the heat, which is this thing here, maybe I should call it Q, that will be force by distance. Now we don't know the force, but we know the distance. But we actually know how much heat is made. How could we work out how much heat is made? That's it. It's the difference between the two. So what is that? 1.85 minus 0.46. 1.39 times 10 to the 5 over 70. So what's that now? 1986 newtons. Oh, well, that's actually 2000 newtons then. You know? No, sorry, what the heck am I saying? 199 newtons. Yeah. That was tricky. You did this one, and did you get that?
I remember 1.39.
Exciting, exciting. But you remember your force at the end? Is there any other way to do it? There is. And I'm going to do it the other way just to check that the answer's right. So the first thing I want to do is get this angle here. So what is tan inverse 20 point, not tan, sorry, opposite over hypotenuse is sine. Sine inverse 20.5 over 70. 17 degrees. Okay, so look at the picture here. This is what's happening. It's going down the hill. Its acceleration should be g if everything is smooth. Sorry, not g, but component of g. This here is g. You can resolve it this way and this way. You don't care about this way. You want to know how quickly it's going down the hill. If this here is 17 degrees, then it means this one here is 17 degrees. So it means, I screwed up my picture here. That's 17, which means this is 17, which makes this one cos, so this one is g sine 17. Yeah, g sine 17 is that one. Trust me on it. It looks a bit weird, but trust me on it. Yeah, what is g sine 17?
2.87.
Okay, 2.87 meters per second squared. Now it won't really go down the hill that fast because what is happening is there's a force pulling it back, you know, the friction. So what I want to do is calculate the A. So do I know the U? I do, it's 0. Do I know the V? I do, it's 10. Do I know the A? I don't. T? I don't. S? I do. What is it? 70. How can I get the A? I could say V squared equals U squared plus 2AS. So the A is 100 over 0.14.
0.714.
Meters per second squared. Okay? Now what did Newton say? Well, Newton said F equals ma. Now, hang on, this is the acceleration, not the weight. So if I want to change this into weight, I just multiply it by m to make it mg. Okay? So the F is mg sine 17 minus this force. I'll call it or. Minus or. That's equal to ma. Okay, so the or will equal m, what's the m here? 920 times 9.81 times sine 17 minus 920 times 0.714. What do we get here? .1982, or if you round that off, that's 1990 newtons. Same answer.
If you minus the acceleration, you get the same answer. No, yes.
If you what now?
Minus the acceleration.
What do you mean?
2.87 minus.
Oh, sorry, that's 1982 you said, was it?
Yes.
Oh, well, you know what the reason is? I think it's the sine 17. We could probably be a bit more accurate on the 17. Was it 17 point?
I think it was 17.02.
I wonder if it would be a bit more accurate if we put in 0.02.
So
Anyways, it doesn't matter, yeah?
about the last question.
Yeah.
You can resolve.
Yeah.
Wait, the last question.
What do you mean?
The turning force. The ladder.
Yes. Oh, is that what you meant by another way? Yeah, you could take the forces and resolve them along the ladder. Correct, yeah. That's fine. Is that what you did? Okay, good. Good. We can do number 3. Then we'll finish. Doesn't matter. We got it. I think in the marking scheme they probably would have done it the first way. A length of wire is connected across the output of a power supply which is adjusted to deliver a current of half an amp through the wire. A voltmeter is connected at the end of the wire to determine the potential difference across it. The procedure is repeated, keeping the current at half an amp, and you have the following readings. So what happens here is you have length, you have voltage, and you have resistance. Now I'm not going to write the whole table down, it's a bit too much. But the first length is 0.1 meters, and then it's 0.2 meters, etc. Okay? And then the voltage starts off at 0.695, 1.41, and that continues. And your first question was to find the OR. Now, don't forget, in the question they tell you the I is always 0.5 amps. So by using the VI OR, would that work? OR is V over I. Yeah, so you just take these numbers and divide it by 0.5. So what's 0.695 divided by 0.5? 1.39 ohms, and then 2.82 ohms, etc. Continues in the table. Yeah? You have to complete the table. Okay, I'm not going to do the whole table. And then you have to graph it. And they wanted you to graph it so that the resistance is on the Y and the length is on the X. And I think everybody had this fine. So here you have the length in meters, and here you have the resistance in ohms, and you plot your points, and you got a straight line, and that's all fine. Yeah? Did you do this one?
Yes.
Yeah. Okay so far? I think you did it as well. Both your graphs are fine. Calculate the gradient, the slope. So obviously I'm just going to roughly estimate it here. I'm just going to use 2 points. I'm just going to use the first 2 points because I have them here in the table. So it would be the rise over the run. So that would be 2.82 minus 1.39 over 0.1. So what's that, please?
$40.3.
40.3.
14.
14.3.
Yeah.
And what's the unit? What's the unit? Correct. Ohms per meter. Yeah. Right. Part 4. I don't know what they were doing. They just gave you 4 numbers and they asked you for the average of them. Four different lengths of wire for 1 mark. So what's the average of these 4 numbers? 3.314 plus 0.315, 316, 315. Yeah, what you got here? Is it 315? Yeah. So the average is 0.315 millimeters. Yeah. And then the last part here is what's the resistivity? So resistance is rho L over A. Okay. On the graph, you had L here and OR here. Now, if you look at this, OR equals rho over A times L. So this slope here, what does it represent? It represents rho over A. Because this is on the Y and this is on the X, so this is the slope. Yeah? So, what did they want? They want the rho. So you know that rho over A equals 14.3. So that, yeah?
Isn't rho over L?
I think I have it right, don't I? Rho L over. There's one way to check.
I mean, the gradient is rho over L times A. No, L. I'm sorry.
Okay, continue? Okay, no problem. No, it's good to ask. So the rho is 14.3a, and the a is pi r squared, and the r is 0.315 over 2 times 10 to the minus 3. So if you just hit that in, we have that part finished. And then we finish with a nice 9-mark Kirchhoff question. Ohm meters. Yep. Lastly, come on, Siva, hang in there. Hang in there. I have a Kirchhoff circuit here. So I'll just write down the 3 equations, okay? So it was going to be, well, do you know what, actually, what's more important is if you can give me the equation. So there's that, there's one there, here, goodness, here, here. What's wrong? 6, 0.1, 0.2, 8. And then this one here is 2.2 volts, 1.4 volts. And this way is I1, and this way is I2, and this way up here is I3. Okay? So let's start with a junction here. So I1 goes in, I2 goes in, and I3 comes out. That's our first equation. Done. Now let's make a loop. Let's start at the 1.4. So you have 1.4 minus 6I1 minus 0.2 I3 plus 2.2 minus 0.1 I1 equals 0. I've started here and I went around back to there. Okay, that's the second equation. And then the third equation, let's start here and go around to the right. So that's 2.2 minus 8I3 minus 0.2, oh sorry, what? Not 8I3, sorry, 8I2 minus 0.2 I3 equals 0. Okay? And there you go, there's your 3 equations. So you just have to solve these 3 equations. I think it was like 1, 1, 1. And then, so the marks, there were 9 marks. 3, 3, and 3. Okay? So the 3 marks at the beginning were for getting the 3 equations right. And then the 3 marks in the middle was the correct process for solving. And the final 3 marks was actually getting the answer right. So what would be the easiest way to solve this one? This has I1 and I3 in it, doesn't it? This has I2 and I3 in it. So we have to first cancel I3 from everything. So this has minus 1. This has minus 0.2. So I should multiply this one by 5. And, oh actually, you know what would be much easier? If I just multiply this one by 0.2. Because then this will have 0.2 I3. This already has 0.2 I3, and so does this one. Do you see what I'm saying? So then once you do that, you minus them. So if I call this A, B, C, you do equation A minus B, and then you do B minus C. When you do A minus B, what letters have you got left? Well, they'll cancel, so you'll just have I1 and I2, right? And when you do B minus C, what do you have? What letters? Well, you'll have I1 and I2 because the I3s will cancel. So you'll have I1 and I2. And then of course you know how to solve this in maths class, it's just 2. So I think the 3 marks here, I would probably guess 1 mark for doing A minus B and B minus C. Then 1 mark for solving this. And then 1 mark for taking your answer, or something like this, I don't know. Anyways, do we have time to solve it? Not really, not really. So, I'll cheat. Our good old calculator friend, mode 52. Right.
Can you get the 3 marks answer if you don't do the steps?
I'm not supposed to give it to you, but if I'm feeling generous, I might. One, but you can certainly check your answer. 1, 1, minus 1, and 0. Okay, how many I1s have I got in the next one? Minus 6.1, yeah? What? Okay. Minus 6.1. How many I2s have I got in the next one? No I2s? No I2s? Are you sure? Okay. How many I3s? Minus 0.2. And that's equal to 1.4 plus 2.2 is 3.6, but you take it to the other side. Minus, why did my equation disappear? 1. So, let's start over. Mode 52. 1. Minus 1, 0. Minus 6.1. I2? 0. I3? Minus 0.2 or 0.1? That's 0.2, I think. And that's equal to minus 3.6. Right. I1? No. I2? Minus 8. I3? Minus 0.2. And that's equal to minus 2.2. Right, so I1 is 0.56 amps, I2 is 0.25 amps, and I3 is 0.818 amps. So I mean, at the very, 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 very least, even if you don't get the marks for this step, you must get 6 out of 9 marks using your calculator, because they must give you 3 marks for writing the equations down correctly. And if you did write them down correctly and type them into your calculator correctly, you automatically get these 3 marks. So even if you used your calculator to solve this, you automatically get 6 out of 9 if you got these equations right to begin with. So this is what I mean by exam strategy. You might say, well, if you're running out of time, if you did this on the calculator, you would sacrifice 3 marks, but in only a couple of minutes you could get 6 marks. Do you know what I mean? So this is more stuff to think about for the final exam. Okay, how many people did the Kirchhoff one? You did? And did you feel like you ran out of time, didn't you? Or yeah, and can your calculator do this? Nice. Okay, that's another thing to talk about another day. Right, so we finished the exam, so we'll go back to the workbook next time then. I'll bring it to class.